Okay, so chapter 10 deals with liquids and solids. It's often referred to as the condensed states. They're combined together, and we're actually going to combine chapter 10 with chapter 11, which deals with solutions. So they're very similar in a lot of ways. But we have to refer back to what gases are like, because it has been a while since we've done that. And so we want to talk about how gases turn into a liquid and solid, because they all do. That was one of the one of the descriptions of an ideal gas, is that an ideal gas is assumed to have no attractive forces between the molecules at high enough temperatures and low enough pressures. But if it was a real gas, it will eventually turn into a liquid and then a solid if you drop the temperature low enough or you increase the pressure enough. So, a low temperature, high pressure, the attractive forces begin to attract the molecules. And so it starts to hold them together like a little magnet. And it turns them into a liquid. And those are called intermolecular attractive forces, IMAF. Okay? As the gas molecules are bouncing around, let's say I had helium. They're bouncing around, moving around, bouncing, wherever they go. Okay? And as you slow them down, they have these intermolecular attractive forces that attract those two molecules and make them stick together and make them like magnets. They stick together and they eventually will turn into a liquid if you drop the temperature enough or you increase the pressure enough. And if you keep going even further, they'll turn into solids and they'll lock themselves in place. That's what intermolecular attractive forces do. Now, there's several different kinds of them. Okay, they refer to the forces between two different molecules. The ones that we're used to dealing with are polar covalent bonds and nonpolar covalent bonds and ionic bonds. Those are inside the molecule. This is between two different molecules, and it would hold the molecules together in the condensed states. Okay, it takes a little bit of energy to break them because they are relatively weak, or at least the ones that are weak are really easy to break. Inside the intramolecular, they are bonded to each other using either polar covalent, nonpolar covalent, or ionic bonds. These suckers are really hard to break, and they are based on electronegativity differences because they are breaking apart bonds. They're breaking the electrons that are either being shared or transferred. You're breaking them apart. It takes a ton of energy. These guys, relatively weak, little amounts of energy. Okay, so the first one we're going to talk about is something called LDF. LDF, they are the weakest of the forces. However, everything has it. The reason why they're so weak is because they are temporary. They don't last very long. What creates them is when electrons are not evenly distributed at every instant in time. And so what you get is a temporary dipole. So you get a situation where the molecule, just for a split second, has one end positive and one end negative. Even if it is a nonpolar molecule, at any given moment in time, it is possible that it creates itself with a dipole. Okay? And if it comes close to something else, an atom or another molecule, it can create a dipole in something else. So it's called an induced dipole intermolecular force, but most people refer to it as LDF because that's a whole lot easier to say. So I have here two hydrogen atoms or molecules, and it's a non-polar covalent bond, perfectly symmetrical. We would refer to this molecule as being non-polar. Okay. However, at any given moment in time, if my electrons all line up over here, closer to that one, I end up with a partial negative charge and a partial positive charge, just for a split second. And if it gets close to this other molecule over here, which is nonpolar, what it'll do is, because the electrons are on this side, it's going to push the electrons over to this side and induce a dipole in that one. And they are going to attract each other because opposites attract, and that is the LDF attractive force. It is temporary. It doesn't last long. It goes away really, really quick, depending on the size of the molecule and the temperature. Okay, so very weak, very short-lived. Everything has it, though. Everything has LDF, as long as it has electrons. It becomes stronger if the temperature goes down because the molecules aren't moving as fast. If they're not moving as fast, the force can be a little bit stronger holding on to them. Eventually, it can make liquids of everything if the temperature goes low enough. And it gets stronger when you have more electrons, leading to greater polarization, meaning bigger. If you have a bigger and a more complex molecule, you get greater polarization and it becomes stronger. And if temperature goes down, it's going to move slower, and so they're more strongly held together. And this is how everything eventually liquefies, including helium. Now, it has to be really cold to make helium turn into a liquid, because it's the closest thing we have to an ideal gas. Okay? LDF, generally speaking, is weaker than the other intermolecular forces as long as you're talking same size molecules at the same temperature. Okay? If you're talking bigger molecules, they're going to have stronger LDF. You have lower temperature, you're going to have stronger LDF. Okay? Dipole-dipole is another version of this. Here's the big thing though. It's with polar molecules only because they have a permanent dipole. The one we were doing before was temporary. Okay? And what happens in a dipole-dipole force is the opposite ends of the molecule can attract each other, so the molecules stay close together, and it gets stronger, again, when you have bigger and more complex molecules leading to greater polarization if the temperature drops. Okay? It is stronger than LDF, again, for the same size molecules at the same temperature because it is permanent. This is what dipole-dipole looks like. And when you get a whole bunch of molecules, you get this right here is the dipole-dipole. These guys are attracted to each other. Okay? The last one we're going to talk about is something called hydrogen bonding. It is an unfortunate name. Okay? It is not technically a bond. It's an attractive force. And it is a especially strong version of dipole-dipole. It's kind of like a subgroup. And it happens when hydrogen is, and I should change this, to polar covalently bonded to NO or F within the molecule. So it's polar covalently bonded to N or F. It's attached to an NO or F. What happens is those three elements are extremely electronegative. And because they're very electronegative, they can pull the electron away from the hydrogen, and because their radius is really small, they can get closer to each other, which means stronger forces because of Coulomb's law. And the hydrogen atom only has one lousy little electron, and so that electron is pulled away and spends almost all of its time by those guys. What you have is, if you have NH, really what you have is you have N with electrons and a nucleus, which is really, really small. And because it's really, really small, it can get close to another atom, another lone pair. So hydrogen bonding gets stronger when you have lower temperature, allowing stronger attraction. If you have more hydrogen bonding sites, meaning more places for them to attract, it gets stronger in terms of the hydrogen bonding, even more of them. If you have organic compounds, so an organic chain is something like carbon, carbon, OH. That's a short chain. If I had something like carbon, 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 OH, that's a longer chain. The more the chain is smaller, makes it a stronger force, because the organic chemistry, the organic chain of it, doesn't do anything for hydrogen bonding. Of the three, and I'm going to put in the weak intermolecular forces, it's the strongest because it's permanent and because the hydrogen atom is able to get very close to the electron pair on another atom. And so what you have is, if you had something like NH, and it's really not an H, it's really more like a proton, and it comes up against something like water, which has lone pairs, it can get really close to those lone pairs. And because it's close to them, that's where you get hydrogen bonding. Okay? That's where it gets really, really strong. The other thing is the hydrogen atom that is polar covalently bonded to NO or F has to initiate the hydrogen bond. It's the one that makes the hydrogen bond happen. because it gets attracted to a lone pair of electrons on something else. Okay? And you'll see in your homework what that looks like. So this is water. Water has 2 lone pairs here. If I put it close to another water molecule, what happens is the hydrogen atom on one molecule is attracted to that lone pair. That is a hydrogen bond. The hydrogen atom here is attracted to a lone pair. That is a hydrogen bond. Water is excellent at hydrogen bonding. Okay, so all intermolecular attractive forces have varying strength, but they're all governed by Coulomb's law, meaning the greater the magnitude of the charge, the stronger the force is. So if you have greater polarization, you get greater magnitude of charge, you get stronger attractive force. If they can get closer to each other, you get a shorter distance between the charge and you get a stronger force. There's 2 things that determine it. Okay? The weak intermolecular attractive forces are LDF, dipole-dipole, and hydrogen bonding in that order. Okay? These substances tend to be gases or liquids at room temperature. Not all of them. Again, has to do with the size and that kind of thing. It is possible for something on an LDF on one molecule to be stronger than hydrogen bonding on a different molecule. So for example, water has hydrogen bonding. If I had something like, I don't know, let's do that, benzene. It's got hydrogens, it's got LDF. It's a pretty big molecule though. Because it is so big, it has greater opportunities for polarization, and it could be, I don't know for sure, but its LDF could be greater than the hydrogen bonding on this guy because it's so much bigger. Not always true. It's kind of like, oh, that's a convenient explanation, but it's basically, the idea is the LDF molecule has to be much larger in size to cause a greater dispersion of charge. Therefore, its force, attractive forces, would be stronger than hydrogen bonding. And the way we know that is it has to do with its physical properties, primarily melting and boiling point. So the stronger the force, the greater the attraction between the molecules of the substance. That's what's holding them together. It leads to greater melting points and greater boiling points. So it takes more energy to break the intermolecular forces holding together the solid form or the liquid form. Thus, the melting and boiling points are higher. Okay, so I'm going to show you real quick. This is CH4. And these are everything in its family with hydrogen. And if you notice, the boiling point increases because this atom gets bigger every time. This one is more polarizable. I'm not even sure if that's really a word. More polarizable because it's bigger atom, bigger radius. Therefore, its boiling point's a little higher. But they're all tetrahedral, they're all 109.5, they're all non-polar molecules. This one is nitrogen's family. And these guys all look like this. You've got N in the middle, or H, or P, or AS, or SB. And they're all trigonal pyramidal, and they're all polar molecules. And again, other than the NH3, as they get bigger in size, they are more polarizable, and the boiling point goes up. Now, this one is different. Nitrogen's higher even than that one, even though it's the smallest of its family in terms of radius. But the reason why is these guys all have dipole-dipole, and so does NH3, but NH3 also has hydrogen bonding, and so it's even higher. Okay? If I were to show you the halogens, again, as they get bigger, Cl, Br, I, their boiling point goes up. However, HF is way up here, even though it's the smallest of the group, and that's because it's not. These guys are all HI. They're all polar. These guys are all dipole-dipole. This one has hydrogen bonding. And you can probably guess what's going to happen when I do oxygen's family. Again, they all have this. They're all this structure. They're all dipole-dipole because they're all polar. And again, as they get bigger, boiling point goes up, but water is at the king of the hill because it's got hydrogen bonding. Okay, so it's all tied to, boiling point is all tied to the strength of their forces.